Alright, it's a time to level up with a problem that's a true test of your algorithmic things. Minimum window Subarray. It's a classic question frequently seen in interviews at Amazon and other top tech companies because it requires a dynamic and efficient approach. The problem is this. You are given two strings, a long source string S and a shorter target string T. Your goal is to find the smallest possible substring within S that contains all the characters from T, including duplicates. The optimal solution for this is the sliding window pattern. To make it super clear, let's think of it like a shopping trip. The long string is the supermarket aisle. The target string T is our shopping list. Our window is our shopping cart. The algorithm has two phases that we repeat. First, we push our cart down the aisle, move the right pointer, adding every item we see. We have a counter to track how many items from our shopping list we have fulfilled. We keep extending until that counter tells us our list is complete. Second is contract phase. The moment our list is complete, we stop. We have found a valid but maybe too long shopping trip. Now we try to find a shorter path. We move from the start of our trip, the left pointer, and put item back on the shelf one by one. As long as our shopping list remains complete, our trip gets shorter, and we update our best record. The moment we put back an essential item that makes our list incomplete, we must stop contracting. With an incomplete list, we go back to the expand phase to find the missing item again. This expand contract cycle is the entire logic. Let's trace this visually. We have a string S and a string T. We need to find A, B, C. Our need count is 3. Our right pointer expands. It finds A, then a B, and finally a C. Our window becomes ADOBEC. It's our first valid window. The length is 6. This is our current best answer. Now we try to shrink. We remove A from the left. Our window is now, it's no longer valid because we need an A. So we must stop shrink. With our window invalid, we must extend again. Our right pointer continues moving, and then it finds another E. Our window is now, it's valid again. The length is 10, which is not better than 6. We try to shrink it. We remove our window till C. Bank B, A, and C was better. B, A, and C is the final answer. The algorithm continues this expand and contract process, but won't find anything shorter. That's our result. Let's check the code together. If S is null, T is null, and S length less than T length, return an empty string. Then initialize left and right is 0, start is 0, minimum length is equal maximum integer, and required size is equal T length. Need is our actual shopping list. A hash map tells us how many of each character we need to find. We extend our window. We grab the character C at that position. We check if this character is on our shopping list. Need contains key C. If it is, we check if we still need it. If we do, that's great. We found one of the items we are looking for. So we decrement our required counter. We then update our shopping list to say we need one less of that character. If we find more than we need, this count can go negative, and that's okay. Finally, we expand our window by increment right, which means our shopping list is complete and we have a valid window. Now our goal is to make this window as small as possible. First, we check if our current window is a new record holder for the shortest length. If it is, we save its start position and min length. We get the character from the left side of the window, the one we are about to remove. We check if this character we are removing was on our original shopping list. If it was, we return it to the list by increasing its count in our neat map. This is most crucial part. After returning the character, if its needed count goes above 0, it means we just lost an essential character that we need. Our shopping list is now incomplete, so we increment required. This will break us out of this inner while loop and send us back to the expansion phase to find our missing character again. Finally, we shrink our window from the left. At the very end, we check if we ever found a valid window. If minlen was never updated, we return an empty string. Otherwise, we use start and minlen of the base window we found to cut out and return our final answer. Each pointer left and right only moves forwards throughout the string as once. This gives us a linear time or n time complexity, where it is the length of s. We can call space complexity or m, where it is the number of unique characters in the target string t. Another essential interview question that perfectly demonstrated the power and elegance of the sliding window pattern. Longest substring without repeating characters. The goal is simple to understand but requires a clear solution. Given a string like ABC, ABC, BB, you need to find the length of the longest string that does not contain any repeating characters. For our example, the answer is ABC, which has a length of 3. Once again, checking every single possible substring would be far too slow. The optimal solution is a dynamic and efficient sliding window. Our tools for this problem will be 2 pointers left and right. To define our window and a hash set. The hash set is the key. It will store the characters currently inside our window and allow us to check for duplicate in constant time. Let's trace with a great example. We start with our right pointer at index 0. The character is A. A is not our set. We edit and update our maximum length. Next B. It is new and edit. And update maximum length to 2. Next C. And it's new, edit. And update maximum length to 3. Our window is now ABC. Now our right pointer move to the next character, which is A index 3. We check our set. Does it contain A? Yes, we have a duplicate. We cannot expand our window anymore. To fix this, we must shrink our window from left until the old A is gone. We look our left pointer at index 0, character A. We remove it from set and move left one step to the right. Character set is equal BC, left is equal 1. Now the duplicate A is gone from our set. With the conflict resolved, we can now add a new A. The current window is BC. A, the length is 3, maximum length is still 3. Our right pointer moves to the next character B, duplicate. Our set already has a B. So we shrink from the left again. Remove left, which is B, and left becomes 2. Now we can add the new B, it's the right one. Current window CAB length is 3, maximum length is still 3. The process continues like this with the window sliding along the slides, expanding when it finds unique character and contracting when it hits a duplicate. Throughout this entire problem, the longest valid window we ever found had a length of 3. And that's our final answer. Let's check the code together. First, we set up our tools, create a hash set called window. And left is 0, maximum length is 0. We started the expand window from 0 with right pointer, it's equals 0. Get the current right character. If window contains the current character, we will shrink the window. And we will remove left character till window doesn't contain current character. Once we are sure our window is valid, we add the current character to our set. Then we calculate the size of our current valid window, which is right minus left plus 1. We compare this size with our maximum length. After the for loop has finished, our maximum length variable will hold the final answer and we simplify return it. Efficiency of the sliding window pattern. Even though we have a nested while loop, this is not O(n) square. Each character in the string is visited at most twice. once by the right pointer and once by the left pointer. This means the time complexity is linear, O(n). For space complexity, the worst case, all characters in the string are unique, and our hash web will group the size of the string. The space complexity is O(n). Classic of algorithm interviews, maximum subarray. This problem is famous because its solution, Cadenas algorithm. It's incredibly simple, clever, and efficient. The problem is this: you are given an array of integer which can include both positive and negative numbers. Your job is to find the continuous subarray that has the largest possible sum and return that sum. For example, in the array -2, 1, -3, 4, -1, 2, 1, -5, 4. The maximum subarray is 4, -1, 2, 1 with a sum of 6. The logic is incredibly simple. Think of it like this. You have two values you are tracking. One is your current sum. This is the sum of the subarray you are building right now. The other is your maximum sum. This is your all-time record. As you walk throughout the array, we add each number to your current sum. But here is the one rule you need to remember. If your current sum ever becomes negative, it's a dead weight. Drop it, restart it to 0, and start building a new subarray from the next number. At every step, you simply compare your current sum to your maximum sum record and keep whichever is bigger. That's it. One test, one simple rule. Let's check the code together. Max will be our all-time record holder, the biggest sum we found anywhere in the array. Current sum is the number of the subarray we are currently building. We initialize both of them with the very first number in the array. Then we started loop from the second element of the array and walk through it one number at a time. This is the heart of the entire algorithm. At each new number, we make a simple but powerful decision. It's better to expand our current subarray by adding a new number, current sum plus numbers e, or it's better to discard our old subarray and start a brand new one with just the current number c. Mathemax Simplify picks the perfect of these two options for us. This ensures our current sum is always the maximum possible sum for a subarray ending an exact position. After we figured the best possible sum ending at our current spot, we compare it to our all-time record max. If our current sum is bigger, we have a new champion. We update max. After the loop is finished, our max variable is hold the largest subarray and we will return it. It's a beautiful O(n) solution. We iterate throughout the input array exactly once. Constant time operation at each step. This gives us fast time complexity of O(n). We only use a couple of variables to keep track of our sums and we don't use any extra data structure that grow with the input size. This means the space complexity is constant O(1). Alright, next up is a problem I already love because I think it was the first medium problem that I truly understood when I was first learning. Container with most water. It's a classic two-pointer problem that looks tricky at first, but has a beautiful intuitive solution. The problem is this: you are given an array of non-negative integer representing vertical lines. Your goal is to find two of this line that can trap the most water between them. To find a potentially better container, we had to move one of the pointer inward. Which one? The golden rule: we always move the pointer of the shorter line. The amount of the water is always limited by the height of the shorter of the two lines. If we move the taller line's pointer inward, our weight gets smaller, but our height is still limited by that same short line. The area can only get smaller or stay the same. But if we move the shorter line's pointer, we take a change. Alright, let's trace our algorithm with the classic example. We'll keep track of our pointer and maximum area we have found. We start at the left at index 0, right at index 8. The distance between left and right is equal 7. The 8 is limited by the shorter bar. The area is 8 multiply 1 is equal 8. Maximum area is now 8. The left line is shorter, so we move it. Now left is at index 1. Right is at index 8. The width is 7. The height is limited by the shorter bar, which is 7. The area is 7 multiplied 7 is equal 49. Maximum area is now 49, a huge improvement. This time, the right line is shorter, so we move right. Now left is equal 1, right is equal 7. The width is 6. The height is limited by the shorter bar, 3. The area is 6 multiplied 3 is equal 80. This is not bigger than 49, so maximum area remains 49. The right line is shorter, so we move to right. Left is at index 1, right is at 6. The width is 5. The height is limited by the shorter bar. Well, they are equal, so height is equal 8. The area is 5 multiply 8, still not bigger than 49. Maximum area remains 49. Since the heights are equal, we can move either pointer. Let's move right. As the process continues like this, the pointer move closer and closer. Always discard the shorter line and recalculate the area. So we saw our maximum area is 49, was found early, and no other combination was able to beat it. When the pointers finally meet, the loop ends and our final answer is 49. We define our tools. Max array is equal 0, left is equal 0, right is equal end of the array. Our loop continues as long as our pointers haven't crossed. Calculate the width of the container. Calculate the height is limited by the shorter of the two lines. Calculate the area of the current container. Update the maximum area found so far. Move the pointer of the shorter line inward and return maximum area. The left and the right pointers start at the ends and move toward each other. Each pointer will only traverse the array once. This gives us a single path solution with a beautiful time complexity of O(n). We only use a few variables to store our pointers and the maximum area. Therefore, the space complexity is constant O(1). Let's tackle another interview staple that you might see in problems related to calendar scheduling or data consolidation. Merge intervals. You are given a collection of intervals, where each interval has a start and end time. Your task is to merge any intervals that overlap and return a new list of clean, non-overlapping intervals. For example, 1, 4 and 3, 7 overlap and should be merged into a single interval, 1, 7. The secret of this problem is to stop thinking about code and start thinking about your daily calendar. You have a messy list of meetings. What is the first thing you do to make sense of it? Step 1. You sort them by their start time. This instantly bringing order to the chaos. Step 2. You merge them. You go down your sorted schedule. If the next meeting starts before your current meeting's block ends, they overlap. You simply extend your current block to cover both by taking the latest end time. If it doesn't overlap, it's a new separate meeting block. That is the entire algorithm. Sort and merge. It's that simple. Now let's see it in the code. We sort the intervals based on their start times, the first element index 0. This allows us to make a simple graded choose at each step. We ask two things: if our result is empty, or is the end of our last merge interval before the start of current interval. If either is true, there is no overlap. If there is one overlap, we simply add the current interval to our result list. There is one overlap, we don't add any interval. Instead, we just update the end of the last interval in our list. We set its new end time to be the maximum of its old end time and the current interval's end time. The performance of this algorithm is dominated by the initial sorting step. Sorting an interval takes O(n) log n time. After that, we have a single loop throughout the intervals, which is O(n). Therefore, the total time complexity is O(n) log n. For space, we are creating a new line to store the merge intervals. In the worst case, if no interval overlap, we will store all n intervals. The space required for the answer is O(n). We are coming off the end of our first 10 questions. In the next video, we will solve another 10 problems with the same patterns. These questions are not popular just for Amazon. They already ask of another company's interviews. If you watch this video to the end, you are lucky. And good luck during your interviews. Don't forget to like, subscribe, and give a comment. See you in the next one. Thank you for watching, friends. Don't forget to like, subscribe, and leave a comment. See you in the next one.